Welcome to your personalized deep dive, into heat and mass transfer. You sent over some really cool engineering course materials, and we're going to try to break them down together. Get to the most interesting stuff.
Sounds good.
Forget about all the crazy equations for a second. We're talking about like real world problems here: pipes, cylinders, even a train station.
Oh, wow.
By the end of this deep dive, you're going to have so many aha moments. Like you'll be able to actually use this stuff to understand how things
Yes,
work.
I like it.
So let's just jump right in, okay? This advanced heat and mass transfer tutorial, it doesn't mess around. First problem. Imagine like this hollow steel cylinder. It's like a meter high. And the inner wall, it's like blazing hot, 150 degrees Celsius.
Wow.
The challenge is to make the outside safe to touch. So it can't go above 43 degrees Celsius. So how much heat is moving through that wall?
That's a good one to start with. It really shows you something important about heat transfer. It's not just about like how thick the wall is. It's also about something called thermal conductivity, which basically means how easily does the material let heat pass through it. And steel, it's a good conductor.
I would have thought, since steel is such a good conductor, that we wouldn't need a super thick wall.
Yeah, that's a common misconception. Steel does conduct heat really well, but in this case, to have enough resistance, to slow down that heat flow and keep the outside safe, we need a pretty thick wall.
So how do we actually calculate how much heat is flowing through?
Well, there's a formula for that. It takes into account a few things: the temperature difference, how good steel is at conducting heat, and of course how thick the wall is. And when you do the math, it shows you even with steel, you need a pretty substantial thickness to get that outer surface to a safe temperature.
So it's not like a uniform temperature across the whole wall, though, right? We can figure out the temperature at different points inside the wall.
Absolutely, you're right. It's not uniform at all. Think about like a metal spoon in a hot bowl of soup, right? The handle gets hot even though it's not directly in the soup. That's conduction. And understanding like how that temperature changes within the wall, that's key to making sure that outer surface is safe to touch.
Okay, let's try something a little closer to home. Literally, imagine a copper pipe, right? It's carrying water at 80 degrees Celsius to a radiator.
Yeah.
How much heat are we losing to the room before it even gets to the radiator?
That's a question anyone with radiators should think about, and the answer,
Okay.
especially if that pipe isn't insulated, a lot.
Yeah. Uninsulated pipes are like a huge energy waster in homes and buildings. So insulation to the rescue. But how do we know how much insulation is actually enough?
Right. There are a few things to consider. First, you've got the heat transfer coefficients. That's how easily heat moves from the water to the pipe to the air. And then, of course, what kind of insulation are we using and how thick is it? What's really cool is that you sent over this MATLAB calculation that shows just how much of a difference insulation thickness makes for the heat loss.
Yeah, and those calculations are like eye-opening. Even a tiny bit more insulation can save you a ton of energy. It really makes you wonder how much energy is just being wasted, in buildings with bad insulation.
It really does. It's a great example of how understanding, even the basics of heat transfer can have a huge impact in the real world.
Okay, let's stick with that pipe example for a sec. Say we want to know how much the water itself cools down as it moves through a 10-meter pipe. How do we even start with that?
Now we're talking about like the whole system, not just the pipe. We need to know how fast that water is flowing. That's called the flow rate. And also the water's specific heat capacity, which basically tells you how much energy it takes to raise the temperature of, a certain amount of water.
So the water's kind of like a heat reservoir.
Exactly. So the calculation involves the heat loss, the flow rate, and how much the water's temperature changes. And this is what engineers use to design good heating systems.
It makes you think about like how they factor in the length of the pipe and the flow rate to make sure that water actually delivers enough heat to where it needs to go.
That's exactly it. They're using those calculations to make the whole system work as well as possible, minimize heat loss and all that.
Let's change gears a little bit. Let's look at some of your handwritten notes. This is where things get a bit more complex. Instead of heat just flowing through a solid, now we're talking about fluid flow inside an object.
Ah, yeah, now we're getting into the Reynolds number.
Okay, Reynolds number, that sounds a little intimidating.
It's really not that bad. It's just a way to tell what kind of flow we're dealing with. Like, is it laminar, which is smooth and orderly, or turbulent, which is more chaotic,
So why does the type of flow even matter? For heat transfer, does it make a difference?
It can, yeah. Imagine water flowing in a pipe. If it's smooth, Laminar, the heat transfer is more predictable. But if it's turbulent, it's mixing everything up, Makes it harder to predict how the heat's going to move.
So even going back to that cylinder, right, that there's fluid flowing through it,
Yeah.
we need to know what kind of flow it is, because that will affect how the heat moves inside the cylinder itself.
You got it. It's another layer of complexity. But it's important if you want to get the calculations right.
Okay, now let's try to put all of this together. We've got our train station mystery. We've got a diagram showing a long, hot pipeline running through a train station. The big question is, how much heat is that pipe losing to the air around it?
All right. Now we need to talk about forced convection versus free convection. Forced convection is when you've got air being blown over the pipe, like with a fan. Free convection is when the air moves on its own because of the heat, like the air rising above a radiator.
Looking at this diagram, it seems like we've got both kinds of convection happening in this train station.
You're right. It can get complicated.
So how do engineers even calculate the heat loss when you've got both kinds of convection happening at the same time?
It's a lot to consider. They have to use different equations depending on whether the surface is horizontal or vertical, and whether the flow is laminar or turbulent. They've got to factor in the temperature difference, the air's properties. It's a whole system,
Yeah, the real world is definitely more complicated than just a simple equation. Okay, get ready for this. We have a diagram with this curve. It shows the heat flux, basically how much heat's being transferred, plotted against the temperature. And guess what? There's a peak, meaning there's a maximum amount of heat that can be transferred. And if you go past a certain temperature, the heat flux actually goes down.
Wait, what? That doesn't seem right.
I know, right? Why would that happen?
This is one of those things about heat transfer that can really blow your mind. It's all about boiling regimes. As the temperature of that surface goes up, the way water interacts with it changes a lot. At lower temperatures, you might get little bubbles forming. As the temperature goes up, the boiling gets more intense. But then you reach a point called the critical heat flux.
So what happens at the critical heat flux?
A vapor film forms on the surface, and that film, it actually insulates the surface so less heat can get through.
Whoa, so even though the surface is getting hotter, less heat is actually being transferred. Because of this vapor film acting like insulation. That's kind of crazy.
I know, and this isn't just some weird science thing. It has real-world consequences. This is what can cause electronics to overheat. Or it can cause problems in, industrial processes where you've got high temperatures.
So knowing about this critical heat flux is super important for engineers.
Absolutely. It helps them design things that won't break down, Keep everything running safely.
Okay, now let's talk about something that everyone uses every day but probably doesn't even realize it. The heat exchanger. It's basically a device that lets you transfer heat between fluids without them actually mixing together.
The best example is your car radiator. The hot coolant from the engine, it flows through the radiator and it transfers heat to the cooler air. That's how it keeps your engine from overheating.
I see in your notes that you have this little drawing comparing two ways of doing this. Co-current and countercurrent flow. What's the difference?
So co-current is when both fluids are flowing in the same direction. Countercurrent is when they're flowing in opposite directions. And what's really neat is that countercurrent flow is way more efficient for transferring heat.
So if you want to get the most heat transfer between those two fluids, you make them flow in opposite directions.
Exactly. And this isn't just car radiators, okay? Heat exchangers are everywhere. Power plants, refrigerators, even your laptop. Understanding this little principle can make you see the engineering that's all around you in a whole new way.
That's incredible. We've covered so much already. Like we started with simple walls and pipes. Now we're talking about, complicated flow patterns, this crazy heat behavior and heat exchangers.
Yeah.
And it seems like there's a whole other world of mass transfer waiting for us.
You're right about that. And that's where we're headed next. We're going to move beyond just heat and talk about how stuff moves and interacts, molecules, particles, all that. It's way more interesting than you might think.
Okay, ready to dive into this world of mass transfer. We're not just talking about heat anymore. Now it's about how stuff moves, right?
Yeah.
Molecules, particles.
Exactly. Think about opening a bottle of perfume in a room. Those little scent molecules, they don't just stay there, right? They spread out. It's called diffusion until you can smell it all over the room. It's like how pollutants spread in the atmosphere. That's all mass transfer.
So it's not driven by temperature differences. It's about differences in concentration.
You got it. And mass transfer can happen, alongside heat transfer, but it has its own equations and stuff. And diffusion is key here. It's how those molecules move, from high concentration to low concentration.
I'm looking through your notes, and it seems like there's a lot of, converting between different ways of talking about concentration.
Yeah, that's true. We got to be able to switch between things like parts per million, a mass fraction, volume fraction, mole fraction. It depends on the problem.
For example, I see this note about carbon dioxide in the air. It says something like 412 parts per million.
Right. That's how we usually talk about gases. But to actually do calculations, you might need to switch that to a mass fraction, which is like how much of the total mass of the air is CO2?
And you've got to calculate it here that 412 parts per million of CO2 is about 0.63 grams of CO2 for every kilogram of air.
Exactly. And once you have that, you can use it to figure out other stuff like density or how many moles there are.
There's another note here about oxygen in the air, saying it's about 21% oxygen by volume.
Right. So that's how much of the total volume of air is taken up by oxygen molecules. But we got to remember that air is a mix of stuff, right? Mostly nitrogen, like 79% nitrogen.
So for calculations, we change those volume fractions into mole fractions.
Exactly. A mole fraction tells you, like, how many of the total molecules are a certain type. So you know the volume fractions, you can work out the mole fractions for air.
And then using the molecular weights of those gases, you can get the average molecular weight of air.
Which is super useful for lots of thermodynamic calculations.
Now, I keep seeing these diffusion coefficients.
Ah, yes. Those tell you how easily something diffuses through another thing. Basically, how quickly those molecules spread out.
And I guess they're affected by, like, temperature and pressure.
Right. Of course. Higher temperature usually means faster diffusion because the molecules have more energy, They're zipping around more.
You've got an example here comparing CO2 diffusing in air versus water.
Yeah, it turns out that CO2 diffuses much faster in air than in water.
Oh, that's interesting. And then there's this Lewis number. I remember that from the heat transfer stuff. It connects the thermal diffusivity with the mass diffusivity.
Right, the Lewis number. It's this dimensionless number that tells you how heat and mass transfer are related in a system.
So, like, if the Lewis number is close to 1, it means heat and mass are being transferred at about the same rate.
Exactly. And that can make things easier sometimes,
Yeah.
calculation-wise.
Okay, now we're getting into some really cool applications of this stuff. You have this diagram of a heterogeneous catalyst.
Yes. Heterogeneous catalysts are those materials that help speed up chemical reactions, but they don't get used up in the process. It's called heterogeneous because the catalyst and the stuff that's reacting are in different phases. Like, you might have a solid catalyst and the reactants are gases.
And I see here, in your diagram, you've broken down the reaction process into steps. Like, first, the reactants have to diffuse to the surface of the catalyst. Then they get absorbed onto the catalyst. Then the actual reaction happens. Then the products come off the catalyst, desorption, and finally those products diffuse away.
It's a whole sequence of events involving both mass transfer and the kinetics of the reaction.
And you highlighted how important the mass transfer part is. Like, it can actually limit how fast the whole reaction goes.
For sure. Even if the reaction itself is super fast, if those reactants can't get to the catalyst fast enough, it's going to slow everything down.
So you can't just think about the catalyst itself. You got to think about those mass transfer limitations too.
Exactly. And that's where things like the Thiele modulus come in.
Thiele modulus.
It's just a number, a dimensionless number that helps you figure out if it's the diffusion that's slowing things down or if it's the reaction itself.
So if the Thiele modulus is high, it means diffusion is the bottleneck.
Yep. The reaction is happening so fast that the reactants can't keep up.
And if it's low, it means the reaction itself is the slowpoke.
Right. They can get to the catalyst just fine, but the actual conversion is taking its sweet time.
It's like a balancing act, isn't it?
It is. And knowing how to balance those things is key for designing good catalytic processes.
Let's change gears again. Now we're looking at steady-state diffusion through a wall. And your example here is water vapor diffusing through a wall in a house.
Now, this is getting into building science. This is about how to control moisture in buildings.
First thing I see here is this saturation vapor pressure.
Right, that's like the maximum amount of water vapor that air can hold at a certain temperature.
And the warmer the air is, the more moisture it can hold.
Right, you got it. That's why you get condensation on cold surfaces. When it's humid, the air near that cold surface cools down and it can't hold as much moisture anymore. So some of it condenses out, becomes liquid water.
You have an equation here called the Antoine equation.
That's how you calculate that saturation vapor pressure.
So you plug in a temperature, and it tells you the maximum amount of water vapor the air can hold at that temperature.
Exactly.
But we also need to know the actual amount of water vapor in the air, right? Not just the maximum.
Of course. That's where relative humidity comes in.
Relative humidity,
Yep.
right? Like 50% relative humidity means the air is holding half the maximum amount of moisture it could hold at that temperature.
Exactly. In your wall example here, we've got relative humidities for both inside and outside the house. And the temperatures, too.
So we can use that Antoine equation to figure out the saturation vapor pressure at each temperature.
And then using the relative humidity, we can get the actual vapor pressure on each side of the wall.
And I see you've got a difference in vapor pressure between the inside and outside.
Right. And that difference is what's pushing the water vapor through the wall.
So to calculate how much water vapor is actually moving through the wall, we need to know something called the permeability of the wall material.
Permeability basically tells you how easily water vapor can get through a material. It depends on things like, is the material porous? Does it have lots of little holes in it? And also something called tortuosity, which is like how twisty-turny is the path for those water vapor molecules.
So a material with lots of holes and a straight path through it would have high permeability.
You got it. That means water vapor can zoom right through. And for buildings, sometimes we simplify the calculations a bit. We just assume that the driving force is, proportional to the difference in vapor pressure.
And that the diffusion rate is proportional to the permeability.
Right. So if you know those two things, you can get a decent idea of how much moisture is going through the wall.
Which is super important for figuring out if you're going to have problems with like condensation or mold in the building.
It is. Knowing this stuff is crucial for designing buildings that are going to stay dry and healthy.
Now I see another familiar term here, the Lewis relationship.
Yeah. This is cool. It links the mass transfer coefficient, which tells you how easily stuff moves across a boundary, with the heat transfer coefficient, which we've already talked a lot about.
And you're saying for ideal gases, the Lewis number is about 1, meaning the mass and heat transfer coefficients are pretty much the same.
Yep. And that can be super handy. It means you can sometimes just use those heat transfer equations to estimate the mass transfer.
It's amazing how all of this stuff is connected.
It is. It's all about, how energy and matter move around in the world around us.
Speaking of connections, let's hop back to heat transfer for a bit. Now we're talking about unsteady heat conduction.
Unsteady means the temperature's changing, over time.
So it's different from those steady state situations where the temperature just stays the same. Now it's dynamic.
Exactly. And your notes here introduce the Biot number.
The Biot number, didn't we talk about that before?
You might be thinking about the Reynolds number. That's for fluid flow. Biot number is different. It compares the rate of heat transfer inside a solid to the rate of heat transfer at the surface of the solid.
So it's about like how important is the internal resistance to heat transfer compared to the external resistance?
You got it. And it tells you whether you can simplify things. Like, can you just assume the temperature inside is all the same? Or do you have to think about how it changes from place to place?
And you mentioned the lumped capacitance method. That's a way to make things easier, right? If the Biot number is small.
Right. Small Biot number means the internal resistance is way smaller than the external resistance.
So basically the temperature inside changes pretty uniformly.
Exactly. You can treat the whole thing as if it's all at one temperature. Way easier to analyze.
But what if it's big?
Then you can't make that assumption anymore.
Yeah.
Then you got to think about those temperature variations.
You got an example here about a student doing an experiment with cooling and mixing.
Yes. And it looks like there are 2 different ways of analyzing that experiment.
So depending on the details, you might need to use different methods to model the heat transfer.
Exactly. It all comes down to knowing what's really going on physically and choosing the right model for the job.
You also mentioned Newton's law of cooling.
Yes.
Yeah.
Newton's law of cooling, classic. It says that the rate of heat loss is proportional to the difference in temperature.
So the hotter the object is compared to its surroundings, the faster it's going to cool down. It's like a cup of coffee on a cold day.
Perfect example. And that principle applies to so many things.
Back to that student's experiment, I see you got a bunch of details about the setup, like the surface areas, volumes, all that stuff.
Right. Those are important if you want to get accurate numbers. It's not just the temperature difference. It's also about how much area there is for heat exchange.
And I guess the volume matters too, right? Because that affects how much heat energy the object can actually hold.
Exactly. Think about it. A bigger object made of the same stuff, it's going to take longer to heat up or cool down compared to a small one. It's got more mass to store that heat energy.
You also mentioned the characteristic length here.
Yes. That's basically the size of the object, but for heat transfer calculations. It's not always the actual length of the object. It depends on the shape and what kind of heat transfer you're dealing with.
So for a sphere, the characteristic length might be the radius.
Exactly. But for something more complicated, it might be some other dimension that makes more sense.
Now, you're doing some calculations here with time and temperature changes. Seems like you're figuring out how long it takes for something to reach a certain temperature.
That's a classic unsteady heat conduction problem. You got to think about how the temperature inside changes over time as it's interacting with the surroundings.
And I see the Fourier number here. What does that tell us?
That's another dimensionless number. It compares how fast the heat is conducting to how fast it's being stored in the object. It basically tells you how far has the heat penetrated into the object over a certain amount of time.
So a bigger Fourier number means the heat has spread further into the object.
Precisely. And that helps you understand how fast the temperature is changing at different spots inside the object.
Wow. We've covered so much. We've gone from like simple walls to this crazy heat behavior, how molecules move, and now unsteady heat conduction. What a journey.
It's been a wild ride, and hopefully you're starting to see how all this fundamental stuff is woven into, like, everything around us.
I definitely have a whole new appreciation for the unseen forces at work, you know.
That's the power of knowledge. And remember, this is just a taste of what's in those course materials. There's so much more to explore, you know? So many more connections to make.
Crazy, right? How all this theoretical stuff actually shows up in everyday life.
It really is, from the way our houses are built to the way our cars work.
So what about our listener, right? Now that they've got this newfound knowledge of heat and mass transfer, what should they be on the lookout for? What are some things they might notice now out in the real world?
Well, next time they're cooking, they can think about all the different ways the heat is moving, right?
Right.
Conduction from the pan to the food, convection in that boiling water, radiation from the stovetop.
Or how about when they're having a cold drink on a hot day? They might notice that condensation forming on the glass,
Yeah.
because the drink is so cold compared to the air. That's mass transfer.
Exactly. And if they're feeling adventurous, they could even, explore the world of heat exchangers. See if they can spot different types of heat exchangers in their house or their car. Even try to figure out if they're co-current or counter-current.
That's a fun challenge. Once you start looking for them, you'll see them everywhere.
I bet you're right. It's amazing how much we just don't even think about, until we start to understand what's going on behind the scenes.
This deep dive has definitely opened my eyes to this whole world of heat and mass transfer.
It's been fun exploring it with you. And to our listener out there, remember, this is just the beginning, okay? Keep asking questions. Keep exploring. There's always more to learn.
Couldn't have said it better myself. Thanks for joining us on this deep dive into heat and mass transfer. Hope you enjoyed it. Until next time.